In this video I will show you how important it is to choose the right combination of near wall mesh and Y plus wall treatment. At the beginning we will start by taking a look at the theory of turbulent boundary layers. After this we will simulate turbulent boundary layer flow in a channel, and I will show you how different Y plus wall treatments behave for different mesh resolutions near the wall. The near wall turbulent boundary layer can be split up into different regions. Each of them has different physical characteristics and can be modeled using different empirical laws. The current plot shows the dimensionless velocity u plus as a function of the dimensionless wall distance y plus. The red line depicts the dimensionless velocity distribution inside a turbulent boundary layer. The dimensionless wall distance y plus is defined as y plus equals y times u tau over nu. Nu is the kinematic viscosity. U tau is the friction velocity, which is also called shear velocity, and is equal to the square root of the wall shear stress tau wall and the density rho. The expression nu divided by u tau is also called the viscous length scale. The dimensionless wall distance y plus is therefore the distance from the wall measured in viscous length. The dimensionless velocity u plus is defined as the velocity u over the friction velocity u tau. As quantities, the dimensionless wall distance y plus and the dimensionless velocity u plus can be used to subdivide the near wall turbulent boundary layer into different regions. The log law region can be found for y plus values above 30. The log law region is characterized by the validity of the logarithmic law over the wall. This is a self-similar solution for the velocity parallel to the wall, expressed here in form of the dimensionless velocity u plus. Kappa and c plus are constants. The log law is valid for high Reynolds numbers flows. Because of the logarithmic nature of this law, plots of the dimensionless velocity u plus are frequently plotted with a logarithmic axis for the dimensionless wall distance y plus. The log law can be illustrated with a straight line. The viscous sublayer can be found for y plus values below 5. In this region the Reynolds shear stress is negligible compared with the viscous stress. The non-dimensional velocity u plus is roughly equal to the dimensionless wall distance y plus. The buffer layer is located in between the viscous sublayer and the log law region. Here, neither law holds, as the viscous stresses and the turbulent stresses are of the same order. Several wall treatments models are available in StarCesium Plus to model the near wall turbulent boundary layer. A wall treatment model, namely the low Y plus wall treatment, the high Y plus wall treatment, and the all Y plus wall treatment, are simply a set of configurations and assumptions to model the near wall turbulence quantities, such as the turbulent dissipation, turbulent production, and the wall shear stress. The low Y plus wall treatment is designed to resolve the whole near wall turbulent boundary layer, including the viscous sublayer, the buffer layer, and the log law region. It should only be used if the entire near wall mesh on the whole wall boundary is fine enough for Y plus to be approximately 1 or less. Special care needs to be taken of the cell directly at the wall to make sure it falls into this range. The high Y plus wall treatment is modeling the viscous sublayer and the buffer layer by using wall functions for the turbulent production, the turbulent dissipation, and the wall shear stress. It is therefore not required that the mesh resolves the viscous sublayer and the buffer layer. For the high Y plus wall treatment to be valid, the cell at the wall should have a Y plus value of approximately 30 or higher. The upper bound depends on the type of the simulation. While there have been successful applications in the marine and civil engineering sector with Y plus values as high as 500, a value of 100 is recommended as best practice for most applications and should not be exceeded without proper validation. The all Y plus wall treatment is a hybrid approach and is designed to give similar results as the low Y plus wall treatment and the high Y plus wall treatment on appropriate meshes. It is therefore a universal approach and allows to mix different near wall cell sizes in the same physics continuum. The cell sizes should be either Y plus less or approximately equal 1, or Y plus higher or equal than 30. This wall treatment is also designed to give reasonable results for intermediate meshes where the cell at the wall has a y plus value which falls into the buffer layer. In the following, we will take a look at an example simulation to demonstrate the effect of the near wall mesh resolution and of the wall treatment on the turbulent boundary layer profile. For this, we will take a look at a simple canal flow geometry. The wall is located at the bottom. At the top, a symmetry boundary condition is imposed. The flow field is initialized with a constant velocity, and periodic, fully developed interfaces with a pressure drop of 1 Pascal are applied at the left and right side of the flow domain. All the meshes were constructed with the directed measure. On the upper left side, the low y plus mesh with a strong stretching of the near wall area is shown. The medium y plus mesh has a lower stretching, while the high y plus mesh has no stretching at all. On the lower right bottom, the dimensionless wall distance and the dimensionless velocity u plus are plotted. The black line depicts the reference solution from a highly resolved DNS simulation. When the simulation is started, we can see that our simulation approaches this solution. The current simulation applies the realizable K-epsilon 2-layer model with the 2-layer all y plus wall treatment. The red dots depict the solution on the low y plus mesh. We can see that the cell directly at the wall has a y plus value of 0.95. The viscous sublayer and the buffer layer are captured by the solution. The blue dots depict the solution on the high y plus mesh. The cell next to the wall has a y plus value of 34. This solution captures only the locular region of the turbulent boundary layer. The viscous sublayer and the buffer layer are modeled by the wall treatment. We can see that both solutions, from the simulation on the low y plus mesh and from the simulation on the high y plus mesh, give similar results in the locular region. On the medium y plus mesh, the cell directly at the wall has a y plus value of 9.6. Such a cell size lies within the buffer layer and is difficult to handle for the all y plus wall treatment. However, the hybrid all y plus wall treatment does a good job here and recovers the solution with low error. We can conclude from this simulation that the all y plus wall treatment is capable of resolving the boundary layer for low y plus meshes and high y plus meshes. Next, we can switch the turbulence model to the realizable K-epsilon model and apply a high y plus wall treatment. We can clearly see from the result that the high y plus wall treatment is not able to produce a good result on the low y plus mesh. This is because the viscous sublayer and the buffer layer are modeled even though the near wall cell size would be small enough to resolve these parts of the turbulent boundary layer. When we choose the standard K-epsilon low Reynolds number turbulence model in combination with a low y plus wall treatment, we can see that the medium and the high y plus mesh are not suitable for this model, as the cell sizes are too coarse. We clearly obtain a wrong velocity profile in the boundary layer. Similar observations can be made for the SST K-omega model. Here with a low y plus wall treatment, with a high y plus wall treatment, and with an all y plus wall treatment, which is capable of handling low and high y plus meshes. As we can see, the medium y plus mesh produces a lower quality solution. From this video we can conclude that our meshes should be designed to either meet the low y plus mesh requirement with a y plus value of the near wall cell of less or approximately 1, or to meet the high plus mesh requirement with a y plus value equal or higher than 30. The appropriate wall treatment model should be chosen, or as a universal compromise, the hybrid all y plus wall treatment should be used.